I would like to talk a little bit about the research of myself. So spatial structure engineering, that's my special field. And what is spatial structure engineering? The most important thing is 3D thinking and 3D approach. But before going to that, let me tell you a little bit more about Professor Hangai. He is the first person who introduced the so-called generalized inverse to the field of structural analysis. Okay? So in 1981, I think he published a paper about the application of the generalized inverse to the geometrically nonlinear problem. And I believe that he is one of the earliest person who applied the generalized inverse to the structural engineering. And in 1986, he also has written another paper with Professor Tanaka on the rigid body displacement and stabilization conditions of unstable truss structures, first in Japanese and also written in English, and the submitted to the Osaka IASS Osaka Symposium. So in this paper, they showed a very nice classification of truss structure according to the property of generalized inverse, and also about the kinematic relations and also statical indeterminacy. Not just in the small displacement region, but also the, let's say, finite rigid body displacement region. Okay, so when I joined his laboratory in 1986, he immediately showed me these papers, and I was very impressed with these theories, and they finally written the PhD thesis on this topic. And I was very lucky that Professor Hangai invited me to write the book together. Okay, so we have published a book on the application of generalized inverse in 1991. So that was a very big, great experience for me. And especially when I learned about the generalized inverse, I impressed with the approach, or say with the way of thinking of generalized inverse. Okay, so this is a linear equation, okay, which is very useful, especially for finite element analysis or something like numerical analysis of structure engineering. Okay, so normally, for example, in high school mathematics, we learn that say we have a so-called inverse for the square matrix. So with this, we can solve the linear equation, but we don't learn when the matrix is rectangular, okay? So we rarely learn about this, and we don't know if there are no solution or if it's too complicated. But in the theory of generalized inverse, they extend the concept of inverse and also solutions. And finally, we can easily have the solutions in such formula. But anyway, it means that we have many solutions. Okay? So application of generalization, it was very, very impressive for me. And say I learned that this kind of approach can extend the field, say, very, very widely. Okay. So by the way, this theory was independently developed by, say, normally three mathematicians, Eric Moore, Arne Bierhammer, and Roger Penrose. Okay, so Roger Penrose was is the youngest person among them, and so it is very interesting for me, fascinating for me to know that Roger Penrose got the Nobel Prize this year, very recently, on the theory of black hole. So actually, say Roger Penrose had written a very beautiful paper on the generalized inverse when he was 24. So, and I enjoyed and I learned a lot from this theory. Okay, and the essence of what I have learned is when people say there are no solutions, that is a start point to find new solutions. So this is I think the essence that I have learned from say learning studying generalized inverse. Okay. So you can find new solutions anywhere. Okay. So for example, maybe you are familiar with this problem. Okay, so for minimal surface, say using soap liquid, say for example, in this case, if you have two rings and if you make a minimal surface, you will have a catenoid. And if you gradually increase the distance between two rings, so normally you just have two disks. And many mathematicians or researchers said that, say, there are no solutions. Okay, so this is a point. Okay, so normally they say that there are no solutions, but actually there are many, many solutions. Okay, so if you introduce the strings, okay, so just to stabilize the solutions, okay, so you can have many, many solutions, okay, between these situations, these solutions, and also even further. So you can go further with the minimal surface solution. So I'm very happy to learn this kind of approach. So and I hope that you can also share share this concept with this presentation. Okay, and say in the field of spatial structures, say I also searched some place to make a kind of challenge, and one of them was the realization of real tensegrity skeleton for structure purpose. Okay, so I proposed tension truss in 1991. But that was a prestressed frame structure, but that was not the perfect tensegrity. But then, say gradually, we have found that the way how to stabilize the big deformation of tensegrity, and in 2001, we successfully constructed the typical tensegrity skeleton that support the membrane roof. So as far as I understand, this is the first example of say application of typical tensegrity frame for the structure purpose. Of course, there are many, something like tensegrity, but say I'm talking the typical authentic tensegrity frame. Okay. Afterwards, later we have another opportunity to design and apply our skills. Okay, so then in 2017 we designed and constructed a tensegrity tower and the pentagonal tensegrity that are supporting the membrane roof again. Okay. So this is, say, one of my, say, continuous challenge, the area of my continuous challenge. And also, say, in realization of these tensegrities, I insisted to use manual pre-stressing method. Okay, so for the realization of 10 security, you need to introduce pre-stress to the frame. And you can use, say, hydraulic jacks or electric motors to introduce pre-stress to the frame. But in my case, I wanted to use only a manual pre-stressing procedure. Okay, so because say manual pre-stressing is very easy to control, and also it doesn't use any, say, unnecessary energy. So in this sense, I think this is one of the way to go in our, say, new century. Okay, so to minimize the use of unnecessary energy at the construction site. So so far, say we were very successful for this scheme. Of course, the amount of the pre-stress, there's a limit in the amount of pre-stress that the one man can introduce. But if you consider the pre-stressing procedure very well, okay, so you can find the way how to do this only with manual pre-stressing. Okay, so these are the my challenge in the tension and membrane structures. And as I have already told you, we are living in a country of many natural disasters, and one of the most severe one, devastating, is earthquake. Okay, so with the earthquake, we have we may have such a big damage in our life. Okay, so as a one of the typical measure to prevent such damage is so-called technology of base isolation. Okay? So if you isolate the structure, especially from the horizontal movement of the ground motion, so you can save your house. Okay? And actually, there have been many ideas have been proposed by many people, and I heard that more than 7,000 patents have been already taken. Okay, say around this technology, so-called in the field of seismic base isolators. But I say one of the company came to me that was something around the 2,000, and they asked me, please. Develop a new base isolation system with us for for the house seismic base isolations. Okay, so that I think that was very difficult challenge, but several months later, I found a new idea. Okay, so among these types of base isolation systems, this one can be realized very cheap, but still there is a space to make it cheaper, because here they need a kind of concave dish to have a recursive action to the base isolators. So I wanted to reduce the cost further, in the concept of this base isolation system, and then finally proposed such system, a very simple system. So I would like to show you some model demonstration. Okay, so what I was thinking was to develop a new pendulum system which is much cheaper than conventional idea. So here I prepared a kind of rail system. The thing is that it has a wider gap in its middle. Okay. So this is very simple system, but if you put the steel ball on this rail, okay, it becomes a pendulum. But this is very simple and this is very easy to make. So I proposed this system to the company and they're very happy with this. And we developed a new base isolation system using this concept. So using this concept, we have developed such a base isolator for, say, timber residential houses. And okay, this is another say photo of say one of the application of this system to the base of a timber house. And we also tested the system with a big shaking table. Okay, this was a full-scale test. And then say we input the say Kobe earthquake ground motion, and of course the house was completely safe during this test. Okay. Here's another example of my work, say, but related to the earthquake. Okay. So during the earthquake, the large span roof facilities like gymnasiums or swimming pools or indoor swimming pools or public halls, okay, so they are lightweight structure. So lightweight structures are less affected by the ground motion during the earthquake. But however, the structure survived. But say, as you can see, such say architectural finishing, especially the suspended ceiling, suspended very high above in the room, are damaged very seriously. Okay, so this is a very big problem for the especially for the place where many people gather. So since most this damage is observed during the earthquake, so many engineers thought that, okay, so we need stronger ceiling, okay, to resist the earthquake. But actually, this is wrong, okay, because if it is a structural component, maybe we can make it, of course, base isolated or make it very strong. But so the ceiling is not the structure. Ceiling is a non-structural component. So so now we are facing this problem. Okay, so that can be overcome just by make it lighter and lighter. Okay, so if you make it stronger, that means you will put more structure members or say rigid heavy members, okay, above your head. This is wrong. Okay, so if it is possible, you can make it lighter and lighter. Okay, and but actually many engineers could not understand my talk or my theory. So I made many experiment using many ceiling materials, okay, and dropped from the height to the dummy head to measure the impact loading. Okay, and with that demonstration, okay, we found that the so-called membrane ceiling was the best material. Okay, So also in the Great East Japan earthquake, which occurred something 9 years ago, we had many this kind of damage to the suspended ceilings. Okay, they say that more than 2,000 places were had the damage. So after that, so I promoted the membrane sealing, okay, for the restoration of the damage. For example, this swimming pool was restored like this, and this one. So this is before the earthquake. After the earthquake, we also had a damage, okay, especially for the suspended ceilings, and they also followed my suggestion. They make it, recover it with this membrane sealing. Of course, membrane sealing has not good for acoustics and thermal insulations, but say if you don't need such effect, okay, so light and light material is the best solution, okay, for this problem. Okay. And also after the earthquake, we had a very devastating tsunami. Okay. So as the spatial engineer, structural engineer of spatial structures, so we also proposed a kind of personal shelters, okay, to save as a kind of last resort who cannot have enough time for evacuation before tsunami. Okay, so we proposed a kind of deployable full sphere, okay, that can be opened on, say, one person, or personal shelter, inflatable personal shelter, like this. And I was also involved in the new building for Department of Engineering in the main campus of the University of Tokyo, this one. Okay, so for this one, say they wanted to have, say, new laboratory space above the existing, the very old building. Okay, so of course, this old building cannot carry the weight of a new extension. So we used the former courtyard, okay, so of the existing building, and also B-shaped column, okay, of this hanging over part to take horizontal, not just vertical, but also horizontal loading of earthquake. And this is interior view of a former courtyard. Okay, so this is the lower part of the new building that are supported above the existing building without touching. And supported by these thick columns newly installed. Okay, so now, so I have more things that I would like to show you, but because of the time now, I would like to finish my talk. So as Mark already kindly introduced you, I have hosted the IASS 2016 Symposium Tokyo. I also invited Toyo Ito and Kengo Kuma for that symposium. I hope that I'm sure that participants enjoy that symposium. And also, I took that opportunity to host international competition for young people under 40 for the new National Stadium, Japan. That was, of course, that was not the real competition for the real new National Stadium, but that was kind of as a counter competition, because during the real competition, they never heard the voice from the younger people. That was the competition was held just for the old established people who got the, say, who already got the higher prizes like a Prestress prizes. But actually, the people you are going to using that the facility was young people, and also the budget was from the tax from the young people. Okay, so we organized this kind of competition for that occasion, and we selected I think 5 very nice proposals from the, I think, more than 60 proposals from the all over the world. Okay, now, so this is I think one of the last one. Okay, so I have 2 slides more. Okay, so please understand that say what I'm doing now. So spatial structure engineering is very interesting, and that is not just for the tension or membrane structures or shell structures. You can apply the approach of 3-dimensional thinking is to any kinds of structures or not just structures, any things. Okay, so I think the most important thing is this 3-dimensional thinking and approach. So now, we are going to organize the 19th IASS Shanghai Prize to be awarded in the Surrey Symposium next year. Okay, and now this Shanghai Prize is open. So if you are under 30, so please consider to join this competition. Okay, that's all my presentation.